People, we're doing well. This is video 3 on integrating by partial fractions. As promised, we're going to get into ones that are not necessarily harder. They're just, more burdensome, I guess. So let's go ahead. This one is already factored for us. We see that there's a linear and there's an irreducible quadratic. So let's go ahead. We have x plus 1 and x squared plus 4. Let's put an a over x plus 1 and a bx plus c over x squared plus 4. Now, in the previous one, we had an irreducible quadratic. Or actually, in the last two, I think we had an irreducible quadratic. Last three, wow. And they've worked out rather nicely. What we're going to see in this one is that it might actually work out a little less tidy. And so let's go ahead and jump right in. We have a times x squared plus 4 plus bx plus c times, sorry, that's supposed to be bx plus c times x plus 1. So let's go ahead and let's let x equal to -1. If we do that, we get 1. And of course, this whole term goes bye-bye. And I'm left with a times 5, or a is equal to 1/5. Now, that means that I have 1 is equal to 1/5 x squared plus 4. And let's go ahead and multiply this out. We're going to get bx squared plus cx plus bx plus c. Now, you should be able to work with fractions, but as I've said before, if you don't have to, why would you want to? Let's sort of close this off. We have our a. So we have 5 is equal to x squared plus 4. That gets rid of those first two terms, but now I need to distribute a 5 across the rest of them. 5 bx squared plus 5 cx plus 5 bx plus 5 times c. Now, there's a whole lot of 5's in there, but that's better than dealing with a fraction. So let's go ahead and collect those terms. We have 5b plus 1 x squared. That's this and this. We have 5b plus 5c x. That's this linear and that linear. And then, of course, the constant is going to be 5c plus 4. Now, that's all equal to 5, or, that's all equal to 0x squared plus 0x plus 5, right? So we have 5b plus 1 is equal to 0, and therefore b is equal to -1/5. That winds up being pretty simple. And then we can set this, and we don't want to deal with this one right here unless we have to, because that has both of the variables, but 5c plus 4 has to be equal to this constant over here. Subtract 4, divide by 5, and you get c is equal to 1/5. So all three of them are 1/5. It's just the fact that b happens to be negative. Now what that means is the fact that we have, let's go ahead and plot the 1/5 out in front, and let's go ahead and put the a over x plus 1. So if I've pulled the 1/5 out in front, that winds up being 1 over x plus 1. And then if I pulled the 1/5 out in front, functionally b becomes -1 and c becomes +1. So I have plus -x plus 1 over x squared plus 4 dx. Now, in the last one, in one of the previous ones that we had, when we had an irreducible quadratic, we had a numerator that just magically was also like a factor of 2 away from being the derivative of the denominator. That is not the case here. And so what we need to deal with is the fact that we're going to have to separate this fraction. And so we have 1/5, 1 over x plus 1, plus 1 over x squared plus 4, minus x over x squared plus 4 dx. So basically, this right here, I needed to be separated, and it became these two right here. Now, that's important because this numerator in its current form doesn't help me much with that denominator. it either needs to be linear or it needs to be constant. If it's linear, then I can basically do a natural log. If it's a constant like this, then I need to do arctan. So I have 1/5 dx over x plus 1. Now this right here, remember I can factor out of 4. This winds up, if I do that, I'm going to get x squared over 4 plus 1. And of course that can become x over 2 squared plus 1. I factored out the 4, and so that's 1/4 dx. But I don't need 1/4 up here, I need 1/2. So what happens here is this right here can become 1/2 as long as this out here swallows up the other factor of the 1/2 and transforms into 1/10. And something similar is going to happen in the next one where I need to change form. This up here, x is not the derivative of that denominator, but 2x is. And if I put a 2 up here, I need to basically multiply the 1/5 that's out in front of this one by 1/2 as well to get 1/10. And what I'm left with is 1/5 natural log x plus 1 plus 1/10 arctan of x over 2. And of course, if you're more comfortable memorizing the formula instead of changing the form, that's fine. I just want, because basically formulas, memorize them, don't memorize them. The reason I continue to make recourse to the method is I want to do it enough times so that those of you who want to make recourse to the method of changing the form instead are at least familiar enough with it to be comfortable with it. And this winds up being my derivative. And that was tough because, again, it was one of those you have to separate, like after doing the decomp, you then have to further break it apart by separating the fraction according to the two terms in its numerator. It's not terribly difficult, and there are actually ones that are even a little less straightforward than that, but we've seen it before, we've seen it several times now, and I'm hoping that as we sort of march forward, we'll be able to sort of work with those and start to sort of acquire that instinct in terms of being able to work those problems. Now, this one, repeated linear and an irreducible quadratic, and so we have x plus 4, x squared plus 4, and of course we're going to wind up, it might be natural log, it might be arctan, but either way, I've just seen an arctan problem with that denominator, so I should be able to do it pretty easily. This winds up being a over x squared plus b over x. Remember, that's how we treat repeated factors in that denominator. And cx plus d over that irreducible quadratic. Let's go ahead and multiply both sides through by those denominators. Now, thankfully, the repeated linear is just x, so cx plus d is not multiplied by a binomial, especially a binomial squared. So that's going to make, obviously, things a little bit easier. We only have one convenient value. Let's go ahead and do that one. If x is equal to 0, then 4 is equal to a times 4, and therefore a is equal to 1. All right, let's rewrite it and start multiplying things out in order to do our coefficient comparison. This, because a is 1, becomes x squared plus 4. This becomes bx cubed plus 4bx. This becomes cx cubed plus dx squared. And, you know, you obviously have a cubic over here and only a linear over here. So 0x cubed plus 0x squared plus 1x plus 4 is going to be b plus c x cubed. Those are your third degree. Now second degree is here, and so I'm going to get d plus 1 x squared. And then of course my only linear is right here. I'm going to get 4bx and then plus 4. Well, 4b equal to 1, that ought to be 4b is equal to 1, and therefore b is equal to 1/4. That ought to be easy enough. So I've gotten A and I've gotten B. Let's work on C. I know that B plus C is equal to 0, and therefore B is equal to negative C, or negative B is equal to C. And therefore, from this and this together, I know that if C is just B's negative, and I know B, then C is equal to negative 1/4. And this x squared coefficient right here, D plus 1, needs to be set equal to this, and I get D is equal to negative 1. So that wasn't really all that difficult. Let's go ahead and set up our integral. We have A is equal to 1. We have B is equal to 1/4, and I'll simplify it here in just a moment. We have C is equal to negative 1/4. So C and D are both negative. So let's go ahead and pull that negative out and transform this positive into a minus sign. And that's going to be 1/4 x plus 1 over x squared plus 4. Let's go ahead and pull the 1/4 factor out in front. And that's going to be 4 over x squared, or 4x to the negative 2. That's going to be 1 over x, and that's going to be x plus 4 over x squared plus 4 dx. Alrighty, well, while that looks like we're going to be proceeding on to doing 3 integrals, again, I need to deal with the fact that this numerator is problematic with that denominator, and I need to go ahead and more fully pull it apart. Now, you have to be careful, because this is actually a negative x and a negative 4 because of this negative standing at bay here. So if you're going to pull them apart, it actually needs to be 4x to the negative 2 plus 1 over x minus x to the x squared plus 4 and minus 4 to the x squared plus 4 because you have to distribute the negative to both of them. Now, from here, we can go ahead and split it up into our separate integrals. Now, the only one that's the least bit difficult probably is this one, but we've seen how we need to change the form of that. So let's go ahead and rewrite it, and we'll start fresh on a new page. Actually, let's go ahead and pull it apart. So we have x to the negative 2 dx plus 1/4 dx over x minus 1/4 integral x over x squared plus 4 dx. Now that one's going to have to change form. And then minus, well, this 4 and that 1/4 can actually cancel, and we'll sort of leave it like this in anticipation of changing the form here in just a second. Alrighty. This one is really easy, right? Let's talk about this one right here. This one, and I like to integrate all of them in the same turn. So I want to sort of, at the same time. So I want to sort of string these along for a moment. This, I need a 2 up here, right? Which means that I need to multiply outside by a further 1/2, and I'm going to get negative 1/8. 2x dx x squared plus 4. That's going to transform that third one into a natural log. But this last one right here, remember, I can factor out a 4 from the denominator and then pop it up in the numerator as a 1/4. But what I recognize is the fact that I only need 1/2. The other 1/2 as a factor can pop out in front, and I'm going to get 1/2 dx x over 2 squared plus 1. Now from here, I can integrate all of them. They are ready, and they are ready to go. So I get negative 1 over x plus 1/4 natural log of x minus 1/8 natural log of x squared plus 4. And I don't put absolute value bars right here because x squared plus 4 is always positive. Minus 1/2 arctan of x over 2 plus c. And that's it. Okay? A little more difficult, right? But let's go ahead and let's move on to the next one. Let's not dilly-dally. Now this one, not factored, but easy enough. It's the difference of two cubes. And I'm left with dx, x minus 2, and x squared plus 2x plus 4. Okay, let's go ahead and do the decomp. We get x minus 2 and x squared plus 2x plus 4. We get a over x minus 2, bx plus c over x squared plus 2x plus 4. Let's go ahead and multiply both sides. And I hope this is getting so familiar that it's running the risk of being monotonous, because that means that you're well on your way to understanding this and having it mastered, rather than the whole kind of got it. Let's go ahead and let's let x is equal to 2. That's going to give us 1. Over here, that's going to turn this term right here, this product, into 0, because that factor is equal to 0. And when I plug 2 into here, I'm going to get 4 plus 4 plus 4. So that's going to be a times 12. So a is actually 1/12. Okay, well that doesn't make me overly happy, but let's go ahead and plug it in. I have 1/12, and that's x squared plus 2x plus 4. Let's go ahead and multiply this out, and we get bx squared plus cx minus 2bx minus 2c. Now, in order to get rid of, like I said before, you should be able to work with fractions, but if you don't have to, why would you want to? Let's go ahead and multiply through by 12, and I'm going to get x squared plus 2x plus 4. Multiplying this first parentheses by 12 gets rid of the 1/12. You just need to remember to actually multiply the second one. Sorry, that's supposed to be 12bx squared and 12cx minus 24bx minus 24c. Now let's go ahead and collect like terms: second degree, first degree, first degree, first degree. And we're going to get 12b plus 1x squared. For this, it's going to be negative 24b plus 12c plus 2x. That's not looking like a whole lot of fun. Plus negative 24c plus 4. Now, just like we've seen previously, this one right here has both variables in it. Now, you can use that one if need be, but since this one and this one are both in terms of a single variable, then I'm going to set 12b plus 1 equal to 0, because there's an implied 0x squared over here. I'm going to set negative 24c plus 4 equal to 12, because there's an actual 12, and that's one variable, c. So I have negative 24, c is equal to 8, or c is equal to negative 1/3. This is b is equal to negative 1/12, and so we have the three values that we need. Now, what that means is that I have 1/12, 1 over x minus 2, minus, okay, let's go ahead and we're going to take the minus from these and factor it out and turn this sum into a difference. And that gives me x plus 4 over x squared plus 2x plus 4. Now, the problem is when I plop this into an integral, in order for the numerator to be the derivative of the denominator, what I need is, I need more than x, but I need less than x plus 4, because the derivative down here is 2x plus 2. So if you're thinking to yourself, gosh, I wish that was x plus 1, okay, we'll make it x plus 1. So let's go ahead and set it up like this, minus x plus 1 over x squared plus 2x plus 4. You just have to have this 3 over here as well. Now let's move on. Let's actually start another page with our integral. And so we have 1/12 integral of 1 over x minus 2 minus x plus 1 over x squared plus 2x plus 4 minus 3 over x squared plus 2x plus 4 dx. Alrighty. Now the first two are going to be relatively straightforward, and it shouldn't surprise any of us. But this third one, kind of like, what the heck do I do with that? Well, let's go ahead and break them apart so we can, treat them independently. I get minus 1/12, but this is going to wind up being 2x plus 2, so let's actually go ahead and plan ahead and call that 1/24. 2x plus 2 dx over x squared plus 2x plus 4. Now, the only thing that this last one can be, and we'll go ahead and combine the 3 with the 12 and call it 1/4, is the only thing that this can possibly be is arctan, which means that we're going to have to use completing the square in the denominator to rewrite x squared plus 2x plus 4 into x plus 1 squared plus 3. And then, just like we've done in the past, we're going to divide through by this number, like factor that out of the denominator. So basically, if I factor that out of the denominator, I'm going to get 1/3. So we'll pop a 1/3 up here, and we've done this enough time to where it's x plus 1 squared over 3, or x plus 1 over root 3 squared plus 1. I don't need this entire 1/3. I simply need to pull it apart into 1 over root 3 times 1 over root 3. So I have 1 over 4 root 3, 1 over root 3 dx, and this is x plus 1 over root 3 squared plus 1, and that is du over u squared plus 1. Now, we're just going to, pretend that I wrote those down. And now this one becomes 1/12 natural log of x minus 2. This becomes 1/24 natural log of x squared plus 2x plus 4. And this becomes 1 over 4 root 3, or if you want, root 3 over 12, if you want to rationalize the denominator. I don't care right now. And actually, neither should you. And we get that. Now, and the hard part was, unlike previous ones, you didn't want to separate just the x and just the 4, right? You got back here, there was x and a 4. You had to see the fact that you didn't need x, you needed more than x, but you needed less than x plus 4, and how to split it up has everything to do with, okay, what do I wish this was based upon what the derivative of this denominator is? And once you realize what you wish it is, make it that, okay? Let's go ahead and do one last one on this video. Now this one has, again, it's another one of those ones with a linear and an irreducible quadratic. And so let's go ahead and set it up. So we have 9 over x plus 1 and x squared minus 2x plus 6. Now, that looks like I might be having to do the same thing with this one that I did with the last one, which is think about x squared minus 2 plus minus 2x plus 1 plus 5 so I can complete the square. But I don't know. We'll see whether that actually pops up. Let's go ahead and just do the decomp for now, bx plus c, and I get x squared minus 2x plus 6. Now, this becomes 9 is equal to a times this irreducible quadratic. Now remember that is another one of those quadratics that's always positive, because think about this is basically the perfect square trinomial moved up 5 units. Let's go ahead and let's let x is equal to -1. And if x is equal to -1, this over here is still going to be 9. It's a constant. But this is going to be 1 plus 2 plus 6. And of course, this is going to go to 0. So you have a times 9. So a is equal to 1. Okay, that's kind of nice. So this winds up being x squared minus 2x plus 6. And this is bx squared plus cx plus bx plus c. Second term, first term, 0 term, second degree, first degree, 0 degree. And we wind up with 0x squared plus 0x plus 9. And we get b plus 1 x squared. And then we get b plus c minus 2x, and we get c plus 6. And all I was doing was just gathering like terms. Well, b plus 1 is obviously equal to 0, and c plus 6 is obviously equal to 9, right? This being the two quadratic coefficients, and this being the two constants. B is equal to -1, c is equal to 3, and I have my three things. And I know now that it's going to be 1 over x plus 1 plus -x plus 1, or plus 3, sorry, over x squared minus 2x plus 6. Alrighty, well, let's go ahead and rewrite that as -x minus 3 over x squared minus 2x plus 6, like factoring out a -1. And once I've done that, I need to do exactly what I did in the last one. I don't need an x minus 3 up here. I need an x minus 1 that I can then multiply by 2. And so when I set up the integrals, it's going to be 1 over x plus 1. And then it's going to be minus x minus 1 over x squared minus 2x plus 6. And then remember, this is actually -x plus 3. So it's actually plus 2x squared minus 2x plus 6, which might be confusing, but just think about it for a second. Now, from here, this is natural log, this is natural log, this is just like in the last one, it's going to wind up being completing the square into arctan. So let's go ahead and we have dx over x plus 1 minus 1/2 2x minus 2 dx over x squared minus 2x plus 6. And let's go ahead and let's turn that into x plus 1 squared plus 5 dx. And let's go ahead and work with that. Now, what I need, obviously, is to change, like these two are perfectly fine. Let's change the form of this right here. I'm going to factor out a 1/5 out of that denominator, and in doing so, that makes this x plus 1 over root 5 squared plus 1. I don't need the 1 over 5, but 1 over 5 is 1 over root 5 times 1 over root 5. So this becomes 2 over root 5. 1 over root 5 dx. This was x plus 1 over root 5 squared plus 1. So this is u squared plus 1 with du up there. This winds up being natural log x plus 1 minus 1/2 natural log, and of course this is an always positive quadratic. It doesn't need the absolute values, plus 2 over root 5 arctan x plus 1 over root 5 plus c. Okay, and you know, and this is like this process right here is a little bit nasty. Like I've said time and time again, if you're interested in memorizing the formulas, then by all means do it. I hate formulas. I think formulas are harder to remember than doing something like this. You already know you already have algebra skills, very good algebra skills. So why not use them instead of, you know, memorizing a formula which can either be forgotten or probably even worse, misremembered. That brings us to the end of this third video. In the next one, we're going to be doing something a little bit different, and so I've sort of left those examples to create a video all in and of itself. If you have any questions, please do shoot me an email. Bye.